And next up we have Josh Liberman from the University of Arizona. Let me just pull this up. Who will be talking about a spatially clipped self-coherent camera.
Hi, my name is Joshua Liberman. I am a third-year PhD student at the University of Arizona, and I will be talking about a lab demonstration of the spatially clipped self-coherent camera. So to start, I want to remind everyone of our goal, which is ultimately imaging an Earth-like planet around a Sun-like star with hab worlds. And so you can see in the simulated image here with the LUVOIR instrument that after post-processing and wavefront control, we're able to detect our Earth-like planet. Unfortunately, the reality looks a bit more like this, where we have speckles and PSF artifacts dominating around our inner working angle, where we hope to detect these Earth-like planets. And this is an image taken with JWST NIRCam. So how can we deal with these speckles? Well, this emphasizes the need for wavefront control. These speckles are caused by aberrations and imperfect optics within our system, and so they manifest as fake planets, essentially, within our final image plane. And we can suppress these speckles using wavefront control algorithms, some of which you've heard about previously. And so further, I want to emphasize that these speckles are indeed quasi-static as opposed to just static. So in this AO lab demonstration from VLT Sphere, they turn their AO loop on and then monitor the AO control region over a period of time around 100 minutes. And if these speckles were perfectly static, then they would subtract out within our control region. But unfortunately, we don't see that. We still have a lot of speckles here. So this emphasizes, and we see this contrast degradation of around a factor of 5. And so we need a way of effectively freezing these speckles in order to best sense them. And in addition to being able to accurately sense these speckles, doing so could also relax these picometer level stability requirements for habitable worlds. And so in terms of a review of current wavefront sensing methods, one such method is pairwise probing, in which we model our DM's response on the electric field. We apply equal and opposite DM probes, and we use these difference images to estimate the electric field. Additionally, you've heard a bit already about the self-coherent camera, which is a relatively straightforward implementation where you put a pinhole in your Lyot stop. There are fewer model assumptions than that of pairwise probing, and the key thing is you're able to, in theory, measure your speckles within a single exposure. And so the self-coherent camera looks something like this, where you have a focal plane mask that diffracts your light outward towards the stop. You have a spatially filtered beam coming through your pinhole, and this will interfere with your speckles to create fringes in your focal plane. And you can use these fringes to sense your wavefront and thus remove your speckles. And so in terms of recovering the electric field, we can perform a Fourier transform on our fringed image. And so you'll see that these side lobes represent copies of your speckle electric field. And this is the Fourier transform of your fringe term. And then this central lobe is the Fourier transform from your Lyot stop. And so the goal is to isolate a single sideband, as that contains your wavefront information. The challenge here is the pinhole position of your self-coherent camera, where we have, when the pinhole is further from your stop, we have these side lobes nicely separated, but if we move the pinhole closer in, they begin to overlap with your central lobe, and then it becomes very difficult to recover this wavefront information. And so as a result, to implement the classical SCC as demonstrated here requires oversized optics, and you're sacrificing throughput. So the solution is what we call modulation, where if you take one image with your pinhole unblocked, you get your fringes, and then you can take another image with your pinhole blocked, and you just get your central lobe. And by subtracting the two, you can effectively isolate your sidebands. And so there are various forms of modulation, some of which we've already learned about, such as temporal modulation, which Spiders uses, where you can block and unblock your pinhole to create these fringed and unfringed images. There's also polarization modulation, where you can place a polarizer over your pinhole to block out one polarization state. We also have the spectral modulation, where you can place a spectral filter over your pinhole and effectively filter out one given wavelength. And so the challenges of these methods are that you can only modulate in temporal modulation as quickly as you can run your optical chopper. And polarization and spectral modulation require extensive calibrations to account for the intensity differences due to polarization or spectral effects. And so here we're presenting a new form of modulation known as spatial. And so in this lovely diagram, we have the initial setup of our SCC, and we then feed our beam through a Wollaston prism, which splits our light into horizontal and vertical polarizations, and we block out one of these two pinhole beams using a knife-edge stop. And so what we get as a result is both our unfringed and fringed PSFs on the same detector. So we're capturing all of the information we need to sense our wavefront within a single image. And so to highlight the lab demonstration of this, we first manufactured stops at Arizona's machining center using a laser cutter. And so because of the slow F number entering our telescope, our stop is correspondingly pretty small, on the order of around 3.5 millimeters. And so our pinhole is very small as well, and so you can just see it when I zoom in here. And so our pinhole separation is just around 2 millimeters from the center of our stop. And so in terms of the back end of our self-coherent camera, it's fed by this telescope simulator that was developed by a former PhD student, Lauren Schatz. And this is a rather complex simulator involving 6 OAPs, and then we have our 1K DM, and our SCC is going to go at the focal plane all the way over here. And one particular reason I'm highlighting the complexity of this system is that early on, when attempting to get the testbed up and running after about 6 years, I accidentally misaligned an optic upstream of the system, and so I had to realign the entire testbed. And so for those of you who have had the pleasure of aligning off-axis parabolic mirrors, it is not the easiest thing in the world. And so following that entire debacle, we assembled our spatially clipped self-coherent camera. So we have, just before this VVC, we have a circular polarizer, we have our stop, and we have our circular analyzer to complete our filtering setup. We then have our Wollaston prism, our knife edge, and then we're using a Hamamatsu Orca Quest detector to minimize read noise. And yes, our polarizer is just before the VVC. And so there's a certain level of satisfaction after hours in the lab of aligning a VVC and seeing a null rise up in your image like a majestic flower, except that this is not at all what it is supposed to look like. So interestingly, when you send light that isn't purely circular polarized through a VVC and then through a Wollaston prism, you get some fun art, which is not ideal for your science. And so ideally, you want this setup where you're sending in the pure polarization and you're filtering out leakage terms with an analyzer downstream. And again, we're able to confirm this weird effect in simulation, where if we simulate linear input polarization through our VVC and send that through a Wollaston, we see this same effect. So our circular polarizer is effectively not circular polarizing. And so here you see our setup for the polarizer, where our beam's bouncing off the DM window, and it's then going through this polarizer through an OAP and then towards our VVC. And so a proposed solution to mitigate this weird flower effect we're seeing is to insert a polarization grating between the polarizer and the VVC to isolate our pure circular polarization state and thus send only that circularly polarized light into our coronagraph. And then when we look at our PSF images, they're also less than stellar. We have these effects you can see from the VVC, that weird flower pattern, but you also have strong aberrations. And the real challenge is that these aberrations are actually unequal between the two PSFs, because after we perform subpixel registration and normalize our images, we still see all these artifacts in our focal plane. And you see here that we attempted to mask out the PSFs in order to perform our subtraction and registration. And so now we can finally look at the side lobes. And we have actually recovered our side lobes within our fringed MTF, which is very encouraging, except that unfortunately we have also recovered them within our unfringed MTF, which is not what you want to see. And our difference MTF looks very noisy, in part because of these difference aberrations. So one key lesson learned is that moving a knife edge back and forth by hand to try and block a beam that you can't actually see, and then relying on noisy difference OTFs with hopes, prayers, and assumptions that you have indeed found the side lobes might not be the most precise method of aligning your self-coherent camera. So we have a few proposed solutions involving incorporating more post-processing techniques into this initial alignment procedure such that we can effectively determine whether or not we've recovered side lobes at a higher SNR. And then also we need to minimize some differential aberrations within our system. So our Wollaston prism has a focusing lens that follows it, and so that means that our two beams are going through two different parts of the focusing lens, and this introduces some non-common path aberrations. And so in summary, we've designed and implemented this spatially clipped self-coherent camera in lab for single-shot wavefront sensing, and we're still working on improving our alignment, characterizing this setup, and working on our wavefront reconstruction algorithm. And so next steps, once we've achieved the wavefront sensing, is to implement this in a wavefront sensing and control loop using the 1K DM that we already have on our test bed. And then also we're planning on installing this on MagAOX for fall 2026 and using it with the PIA complex mass coronagraph that you can learn more about in Elena Tanucci's poster. So, thank you.
Any questions for our speaker? I'll start. What are the manufacturing tolerances that you need on that pinhole that you guys got manufactured at the machine shop at U of A?
Yeah, that's a good question. I believe we asked for around 0.02 of an inch in our manufacturing tolerances, which I can't remember the conversion to millimeters. But it was very challenging having this pinhole manufactured. I think this facility was the third or fourth one I went to, and finally they said that they could do it. So,
do you think that those tolerances were good enough?
I'm not sure, just because at the moment I think we're dominated by these other
factors.
Yeah.
Okay.
Thanks.
Any other questions? All right. Well, let's thank Josh again.
Can I make a quick announcement about And just before the lunch break, for the early career researchers in the room, on behalf of the local organizing committee, I want to promote this workshop for early career researchers in instrumentation. It's coming this October at the University of Arizona. And if the other local organizing committee members in the room wouldn't mind raising their hands just to see them, feel free to talk to any one of us for additional questions, and you can scan the QR code here to apply. Thank you.
Thank you so much.